Our next session, you have to hear from me a little bit more, but fortunately also Jason Furl. We're going to be talking about tendon impregnation and strengthening of a post-tension segmental bridge. Now, Jason Furl, he's a graduate of the Pennsylvania College of Technology. He's a project executive at Structural Technologies. He has 21 years of construction management experience. His expertise spans concrete, masonry, structural steel, post-tensioning, cathodic protection, and waterproofing systems, along with heavy lifting and rigging. Notable projects include the Woodrow Wilson bascule span lift, featured on the Discovery Extreme Engineering, and the Leroy Selman Pier remediation.
And presenting with Nick here. So Nick Amico is the South Atlantic Major Bridge Lead with HDR in Charlotte, North Carolina, with 20 years of experience specializing in post-tension segmental structures. He holds a bachelor's and master's degree from Virginia Tech. He's a licensed professional engineer and actively contributes to the industry committees with ASBE, PTI, Lieutenant Colonel in the Army National Guard. Nick has 30 years of service and was the engineer record for key preservation work on the Wando Bridge.
All right, thank you, Jason. So we're going to be talking about today PT preservation and rehab on the I-526 Wando River Bridge. First, we got our continuing ed slides. You saw them already on the last presentation. We'll skip right through them. Copyright materials, same as before. These are our learning objectives. I want you guys to get out of this, but I'm going to jump ahead just to save a little time. All right, here's our agenda. A lot of you may already be, some of you may already be familiar with the I-526 Wando River Bridge. We have been working on this bridge since 2016 when we had our first tendon failure on the structure. And we did present at the PTI convention in 2020, obviously covering only the work that had been done up to that time. Since it's been several years and our audience has changed, I do think there's value in going back over briefly some of that work, but we're not going to get in near the amount of detail on that. We can talk later if you're interested in more detail on it. But that's what I'm going to refer to as phase one. And I want to make this just for clarification. So that previous work was actually done under the partnership between HDR as the engineer and Fresnay as the contractor. And the majority of what we're going to talk about today is what I'm going to refer to as phase two, where HDR and Structural Technologies were partners. So we're going to talk through some of that previous work. We're going to get into the impregnation, which is what we worked on with Structural Technologies, and then some strengthening in one of our spans. All right, let's jump right into structure overview here. The button moves. There it goes. All right, the Wando River Bridge is located here in South Carolina, just on the north side of Charleston. It moves a little slow with the button. Connecting Daniel Island on the, there we go, Daniel Island on one side to the rest of the country on the other. Right here adjacent to the bridge, what I got circled in yellow, that is the Wando Welch Terminal. That's a key factor of this bridge. This is the largest port facility in the South Carolina port system. It can handle up to 3 Neo-Panamax vessels. Each can handle over 20,000 containers. And being right next to that bridge, you imagine it's a major user of this structure. To add to that, the Wando River Bridge is one of only 3 parallel structures that crosses the Wando and Cooper rivers. The one to the south is the Ravenel Bridge, and that's when you think of Charleston. That's the one you think of, the big cable stay. And the one to the north is also a Wando River Bridge, but much, much smaller. Of the 3 crossings, the Wando carries about 40% of the total traffic, but more importantly, it's nearly 90% of the total truck traffic that crosses those rivers. So you can see how economically important the structure is to the whole region. It was built with segmental technologies, post-tension segmental construction. The approach spans were span by span. The main span unit was balanced cantilever. There's a combination of internal external tendons. We've got 600, between the 2 parallel structures, 600 external draped longitudinal tendons and 792 internal longitudinal tendons and a whole bunch of transverse tendons that I didn't bother to count up. All right, I mentioned the approach spans are span by span. They used a technique that we don't see very often anymore, thankfully, in which each span was erected simply supported. The post-tensioning and the span being erected was coupled to the post-tensioning of one that had been previously erected. They left about a 2-foot gap between the two spans, and then stressed across the open joint. And that was made possible because of the use of this wedge right here. I can't see that red light, but use of that wedge right there, which is in between the bottom slabs of the two adjacent spans, prevented the spans from translating, but allowed them to rotate. And so essentially you get a continuous for live load type condition. After they stressed the tendons for all 6 or 7 spans, filled the closure pore, they added one more set of tendons in there. Again, you have really only one set of tendons that's been installed in a continuous condition. All right, so that leaves us with 3 challenges, really. First off, in the image here, you see only one tendon anchor. That's because all the rest of the tendons are anchored with anchors or couplers that are buried inside the closure pore that's right in the middle of the pier. Second, that one tendon anchor that you do see is for a tendon that goes up into the top slab and doesn't come back into the cell of the box until about 2 segments later. So there's no way to easily remove that tendon without damaging the structure. And then third, this structure was built before the broad requirement for future post-tensioning be incorporated into design. So there really wasn't any accommodation for future PT in these approach spans. All right, the main span unit mentioned was cantilever. They did use the same erection truss that they used for span by span to facilitate it, supported by temporary piers. But other than that, it was what you typically expect for cantilever construction. We were trying to get to clarify the sequence of closures and such to finalize our models. So we scoured the region looking for construction photos where we could. So the one on the left here is from some office building. They happen to have it up on the wall. And the one on the right is a guy who actually worked on the bridge and who we found had a reel of slides and took us up in his attic. And think Christmas Vacation. That's literally what that photo is right there. All right, and then just a shot of the post-tensioning from the original contract drawings of the main span unit. And some minor changes, well, kind of major changes going into construction. There's actually 2 fewer external tendons that were actually constructed, and they changed the path quite a bit, with one of those tendons being high throughout the full portion of the backspan there. All right, so we're talking here today because we had some issues with that post-tensioning system. So in 2016, we had our first rupture, the one shown on the left, and that's what kicked off all the evaluation and the strengthening that we've been working on for the next 9 years. And then the one on the right was another rupture that we had in 2018. Both of those did occur in the same location, and we'll get into each of them in just a minute here with previous work. So obviously the first thing when you have tendon rupture, you got to replace the effect of that tendon. We got in there and installed 2 supplemental tendons in each structure because we weren't sure yet what the condition was of those structures. So we went ahead and installed the supplemental tendons over there. And then we replaced the tendons that had ruptured. We were very lucky in that the tendons that ruptured, they were the 1,000-foot long tendons that were in the main span unit, and those are the only tendons in the bridge that you can actually remove and replace in kind. It's also the only section of the bridge that had holes that we could use for future post-tensioning. Now, 2018, that rupture, there was a theory that fatigue may have played an issue in it. So out of abundance of caution, we did shut that structure down for just a few weeks while we could evaluate that. Did some metallurgical testing and did confirm that fatigue was not a player in that. But we did use that time with that structure shut down to seal up the slab and fix some other issues. So obviously South Carolina wanted to know what happened and what's the condition of all the rest of the bridges. So looking first at the M1 tendon, that's the one that failed first. We did, of course, visual observations, corrosion potential, corrosion rate, a lot of stuff that Travis talked about, all that battery of grout tests, and then material testing for both the duct and for the tendon. And we found, away from the structure location, the strand was in actually pretty good condition. The grout itself wasn't perfect by any means, but it was still a high pH grout, and it was protecting the tendon as intended. Very different story at the rupture location. That lower image is really key here. That is a piece of grout that we found on the floor at the rupture location. You notice it's got the top level surface there. That was the top of the grout that was in the duct. And you barely see an impression of a wire in it. The grout, the tendon was completely unprotected. It was in a void through the high point of that deviation. It had leaks in that diaphragm, so the pH was very low due to chlorides coming in with the water recharge. Now, looking further away from in the rest of the bridge, we started obviously with visual inspections, which included 300 bore scope inspections across the two structures, and then we found in the process 2 leaking segment joints, a slack tendon in span 16, which we'll get into here in a minute, and then some slack strands, but they were from construction and ultimately not a big issue. The other piece of this was magnetic flux testing. What this really is magnets that are on a steel frame, a rolling steel frame that can run along the free length of the tendon. Those magnets induce a magnetic field that leaks at points of discontinuity in the strand where you have wire breaks or corrosion. And then you can use that, you can measure that in real time and correlate it to an amount of section loss. And it's sort of similar looking little device. Capacitive probe inspection also runs along the free length, but here we're looking with issues in our grout. So we're looking for grout issues like voids, water, white paste, soft grout. When you do find something, you can only see a little over an inch into the grout volume. But when you do get to a location of concern, you can rotate it around the duct to get a cross section of what's at that spot, and then take multiple slices with the device along that length and get a volume for that anomaly. And then we also did some modeling and some limited load rating. And really what we were trying to do here for South Carolina, these segmental bridges themselves generally very redundant systems. We wanted to provide South Carolina with an understanding of how the bridge was performing and some operational guidance. How many more tendons can we lose before we have to start shutting down the bridge? So that was another key piece of this analysis phase. Now, during that phase, we did find 2 more tendons in the main span unit. Again, these are those 1,000-foot-long tendons that span through essentially 5 spans that were corroded and needed to be replaced. Which raised the question, how do you remove a tendon that is 1,000 foot long and carrying roughly 700,000 pounds of force in it? There is an approach that's been used many times in the past where you basically clip it wire by wire in locations in a way that balances the force change on either side of deviators and diaphragms. But in this case here, we had a tendon that we knew was corroded in a high point, very large void, and we didn't really want people right there next to it and doing this sort of work. We were looking for a safer way to do it. So working with Fresnay, we came up with a method using a system of 4 remotely controlled power saws that were strategically located to, again, balance those forces on either side of the smaller deviators and then use the larger diaphragms to handle the out-of-balance forces. So nobody had to be in the bridge, or at least in those spans at the time that we were doing that. All right, I mentioned we had a leaking segment joint. What we believe happened here, this is a location with low compression, based on our models that had leaked in the past. We believe the client saw cut that joint. There's evidence of saw cut there to be able to put a flexible seal inside that to prevent the leak. Saw cutting it removed enough material between the top slab of a flexible segment, because it's just typical segment, and the top slab of a diaphragm segment. So that top slab is quite a bit more stiff, and then with that loss of material there, it just it eventually to continue to deteriorate and started chewing itself up, and you could see the slab come down at you, inside the bridge as truck traffic went over. So we designed a steel frame to stiffen up that the more flexible slab. But of course, it's designed as a one-way slab. It carries out load to the webs. It's not designed for that frame. So we also had put a precast drop slab in there to give it the ability for two-way action. And then span 16, so this is one of the approach spans, and the area I got boxed in blue there on the right, you could reach up and wiggle that tendon. That's not how you want to see your tendons. Now that tendon drops into the bottom slab and comes up at the far end of the span, and it was fully taut at that end. So it was redeveloping within the bottom slab. Now this tendon is coupled to a tendon in the adjacent spans on either side, and there's no way to remove it. And again, there's no way to simply add post-tensioning, or at least not easily. So we had to come up with a way to restore the effect of that tendon without impacting traffic. And so what we came up with is two tendons, where the first tendon anchors in the adjacent span, called span 17, goes up and over the pier, and anchors in the bottom span 16 there. And then the second tendon overlaps it, doing the same thing, going the other direction. So the benefit was all of our anchor blocks are on the bottom slab, so we could do all of our work. We didn't have to punch through the top slab to do this, so we could keep traffic on the bridge. We restored the vertical component of the post-tensioning, of the drape post-tensioning, because we put a drape tendon in there. And then we provided redundancy for those tendons in the other spans that were coupled to this tendon. And key is that we enabled the installation of future supplemental tendons should they ever be needed. You can see the diaphragm that we ended up putting in has accommodation for 5 more tendons in that span. All right, and now we get to phase 2. So we had a better understanding of the condition of all the post-tensioning, but also the areas that we were concerned with. We wanted to freeze the condition of where we're at. We wanted to stop any further corrosion. First thing we did, you got to stop the water. We did a PPC, polyester polymer concrete overlay. It was awesome. It dried up everything, all the leaks that we were aware of. But the next thing was we wanted to add some additional protection to the tendons that we still had. So we used the Post-Tech PTI system from Vector Corrosion Technologies. And this is, it's a low viscosity hydrocarbon silicone polymer resin that gets injected into the tendons. And it travels along the interstitial spaces, between the wires and between the strands and the grout. And it just forms a film on the exposed steel surfaces there to protect the steel, and also soaks into the grout around it to give it some long-term protection envelope. We actually started looking at this in phase 1 because we were like, we've got these couplers. How well does this work going through the couplers? So we tried it out. It worked great. We were able to pump through the couplers. We were also curious about that condition where you have the tendons going up into the top slab. How well was this going to work? We also need to know how much volume is this really going to take to help us kind of estimate out what the cost of this might be. So we did this in a pilot project in phase 1, and in the first part of phase 2, or structural technologies was actually implementing that. So we identified 470 locations for impregnation between the two structures based on that phase 1 analysis. And we only did external tendons. There is some testing that shows that this can reduce the bond between the steel and the concrete. That's of interest if you're counting on that as part of your ultimate moment capacity. But we're using external tendons, so that didn't play in. So we used it for all external tendons. We don't really have any indication there's any issues with the internal tendons. So we had 4 conditions. We did the tendons that have the couplers, tendons with exposed PT anchors, and then the full length of approach and mainspan tendons. And there, I'm going to turn it over to Jason.
All right, so as far as implementation goes, you can see it's a pretty long structure, and what looks like land in the top corner is actually a bunch of swamp for about a quarter mile. So there isn't a whole lot of access outside of the Daniel Island side. So with that, did I do something wrong? Our first order of priority was to get access. So we picked a location that was used previously for repairs. There was only one access hole on one side, and we decided to mirror that on the other side, build an access scaffold that would help us just get up there. We actually put a hoist on this to really help us get all of our equipment, materials. We did a lot of impregnation, so there was a lot of 5-gallon buckets that had to be brought in there. And I'll just call it mileage. We really cut down on the mileage that the guys had to walk. And then in addition to that, we got some battery-powered electronic carts just to keep everything, because our theory was that you want to bring the experts to the opportunity. You don't want them exhausted by the time they get there. So we cut down a lot of miles for the guys. just based on this. Plus, this is had more of a police presence. In the last presentation, you guys talked about the vagrants who like to get in the bridges. And if you're coming in and out, we definitely found evidence of people outside of us getting inside the bridges. So we set up a few trail cameras set with cell phone technology to help see when we were getting invaders. But this area right here, we were able to actually secure the bottom of the scaffold, lock it all off, put deer cameras at the top, and there was a police presence there. There's a big tennis court in a stadium right by this, which also made it really good to accept deliveries. So then we're going into mock-ups. So as Nick had mentioned, we weren't involved in the first phase, and for us, we had to have a better understanding of how it worked. And for the folks from Vector, we relied a lot on their experience of what they did in phase one, but it was fairly limited. So what we had to do was see on a more widespread case, what are we looking at? Because one of the conditions that we had is we couldn't have external leaks. We had to make sure that this impregnation fluid wasn't leaking into the water, causing staining on the bridges. And at the same time, because this is a really nice area, we had to see the aesthetics of whatever we were going to seal it with and make sure it wasn't aesthetically unpleasing. I know that sounds a little bit funny for a bridge, but this is there's a lot of money in this area. So you can see all the suds here, just like how you would check a tire when you suspect a leak. One of the first things we did is our folks from Vector would start to air test, and we would spray soapy water on the outside. And one of the first things I did was freaked out and thought we were going to have to coat the entire bridge because there were leaks everywhere. Every single chair, weep holes, every joint leaked and bubbled up with soapy water. And I got myself some composure, and we realized it's like, this material is very thin, but it isn't as thin as air. So let's actually test it out. This will be a good opportunity for us to see, in what cases does it actually leak the fluid when it's put in. And it was mentioned in the last presentation that prior to 2000, issues with grout, issues with joint detailing, that's really what we found is most of these joints were not properly epoxied. Much of the ductwork was just spliced and coupled together. It leaked air everywhere. We probably had to seal up as much on the inside as we did the outside. And we were pleased to find that we were able to actually isolate the locations where it was likely to leak, and we came up with a proactive sealing plan based on that. And then we found a few areas that we didn't expect it to leak, but it was a good thing we caught it when it was, quote unquote walk-up work, and we weren't on a snooper truck under lane closures at night trying to figure out where it's leaking, with traffic whizzing by. So the condition ones, as Nick had mentioned, there were a lot of these where you were going against a coupler. For me, the issue you find there is it is sort of an issue when you're trying to push fluid past a coupler and uphill without filling the rest of the tendon, right? So instead of just doing a limited scope, you could end up filling up the entire tendon before you get across it. And I'll show you later, we had some really smart guys from Vector we brainstormed, and we came up with a way to do a push-pull method by pressurizing the impregnation fluid and then vacuum assisting it across where we could pull it across the coupler and make sure that we got it on the exit ports. But occasionally we get what you see on the left-hand side, I had it circled. That's what it looks like when the fluid decides that it's easier to go outside of the bridge than to go across the coupler. And then on the right-hand side, you can see we did manage to find a fix and a seal that worked really well. It blends right in with the concrete. So to the point of the aesthetics, we did find some products that we could use to get that taken care of pretty quickly. And it was actually pretty easy to clean up as long as you were proactive about it. Then we had our condition 2. Our condition 2 was also across a high point, but in these, we were able to actually, we didn't have to go across a coupler, and in many cases we were able to get to the face of the tendon. And this material is really good. We were able to drill in You know, as he had talked about with testing the grout, we were able to do similar sized drill holes and actually impregnate, but when you can get right onto the end of the anchor, we knew we could get the anchor and the wedges a good bath of the material to make sure that was coated well. And when you have access to every one of those anchors, it's able to follow the path and get into the high point voids. And then we had the condition 3s. These are the full length. So one of the things from a cost perspective from the state, they didn't want us turning those condition 1s and condition 2s into condition 3 where we had to fill the entire tendon before we actually filled the high points. So that's where that push and pull method came into play. And what was happening here, as you can see, there were multiple joints as those tendons would go through the deck. I have it highlighted there. Every one of those segmental joints was a potential leak path. And then in condition 4, these were those long mid-span tendons, the 1,000-foot long. Very similar to the condition 3, except about 3 times as long, 10 times as long. So on that one, we really needed to focus on that push-pull method as well. And then one of the other challenges that we had was drying the tendons. As Nick had mentioned, they had to put a methacrylate coating. They did all sorts of things to the deck to waterproof it. But there was water in the tendons, and it's a high humidity environment. Because the duct wasn't sealed up well, there was a lot of moisture in many of the ducts. And the initial plan, the way it had been done before, required some very invasive equipment to heat and to dry those out before we impregnated. And we started to look at what it was going to cost to get this to the mid-span. We were looking at 480 volt, 200 amp service in order to power all that equipment, which when you think about getting that a half a mile away, that's a lot of cable. I think we figured it was close to $5 million worth of cable that we were going to need to purchase and then lug through there. We tried to get house power, but we had a little bit of a supply chain issue at the time, and we were told that we were about 7 years out from getting a transformer that could help us put an actual permanent power in there. So we ended up coming up with a method that was pretty good and this saves the state money and actually helped reallocate funds towards other repairs that they wanted to make while we were out there. But we ended up using a micro drying system where we were able to use these pancake compressors and used moisture separators on them. We realized there's not a whole lot of air that you have to push through the tendon. And we could leave these on through the weekend, and we would come back and do another moisture test, and tendons were all dried out. And we had some 110 power that was already run through the bridge that was able to power all that. So it was a really good solution. And somebody had mentioned that the vagrants were using air conditioning, and we also noticed that it was hot in these bridges in the summer. When we put these chillers in, these were the biggest chillers that we could actually fit through our 3 foot by 3 foot access. But what we noticed is they were able to drop the humidity enough to actually dry the tendons out as well. So for the months where it was really hot and we had to run those, in the spans that we ran them, we noticed that we had 0 drying that we had to do, no supplemental drying. So it's just a good note that there's a quality correlation to the safety issue that we had for our guys. And then this is a picture here of the pressure pot setup. So this was a good way to make sure we had some quality control on what we were putting in, but we'd pressurize the impregnation fluid, put it in these pressure pots, and then we weigh the pots as well. So we had both we lost this volume of fluid, we were able to track the buckets, but we also knew it by weight. And then on the other side, you can see the vacuum assisting where we were pulling it as well, which helped to make sure that we put the impregnation fluid where it was supposed to go and not throughout. And I believe it's back to you after this.
Thanks, Jason. All right, so unfortunately, we did have an issue in the impregnation process. While impregnating, it was close to one of the last tendons on the project, if I remember right. The team told me they heard a loud pop. It sounded like a gunshot going off inside the bridge.
A cannon.
A cannon? Okay. Didn't initially see anything. Obviously stopped impregnation operations, but then went for the weekend. It took a couple days, a couple thermal cycles, came back and found what you see here, which is the duct, which is pulled about 2 inches away from the diaphragm face. The upstation, this is a tendon that drops into the bottom slab, just like the other approach span that we had talked about. And the other end of it appeared to be fully taut. And there's no evidence of water infiltration or corrosion on that tendon. But again, it had all the same challenges. Now, what we think happened here, I want to be very clear, this is not an issue with the post-tech material. This is actually a situation that we thought was a possibility, and we discussed it with the client beforehand. What we believe happened is that tendon had corroded behind the anchor, inside the diaphragm, and then through the bond with the steel and the diaphragm concrete. Diaphragm's like 9 feet long. That's what was holding the tendon in place. So when we inject it with the corrosion, anti-corrosion oil, it lowered the bond just enough that it released a little bit. That was something that we discussed with South Carolina and with Structural Technologies before we went into this, and it was a remote possibility. Do as many tendons as we did, and it comes up. But we also did not want to rely on a tendon that was going to be in this, be restrained in this condition to begin with. So the decision was, we know how redundant the system is. If it happens, it happens. We'll fix it and move on. So anyway, again, the first thing we did was the expedient condition ratings. We already had the model set up, so this is extra expedient. But giving the client an understanding of how much how much redundancy do they have? What sort of operational guidance should they follow here? How many more tendons can we lose before we have to start adjusting traffic? Again, this is a very redundant structure, so we showed that we could lose multiple tendons before we actually had to shut that bridge down. But that relies on the assumption that the other tendons are in good shape. So the next thing we did was work with Structural Technologies and their VibraTest system, got in there and checked the tension that was being held by the other tendons in that span and the spans on the adjacent side of it. And basically what this is a system of accelerometers that measure the natural frequency of the tendon. Now, knowing the tendon mass and the free links, you can back out what the force in that tendon is. It's the same harmonic equation that at the fundamental levels anyway, that you would use for the acoustics of a guitar string. We found that the tendon at the ruptured end was still holding about 26% of guts. And so it was still holding some force, and at the other end of it, it was around 64%, right where we expected it to be. And all the other tendons in that span and the adjacent span were all holding about 64% of guts. So that's, again, exactly what we were hoping to find. So next was we need to go design the repair for this. We wanted to restore the original permanent stress condition. We need to restore both the ultimate and shear and torsion capacities. Again, we did not want to hinder any future strengthening that may have to be done on the bridge, and we had to minimize impacts to traffic. We had a big benefit here in that we had 2 extra tendons in this span than what we had in the other approach spans. So we were a lot further from the principal tension limit and not as much concerned about getting that drape portion of the tendon restored. So we were able to, we'll see in a minute, but we were able to go with a much simpler solution than what we showed previously for span 16. We also bounded our design on the assumption that that tendon was completely lost and completely intact. So we wanted to be able to replace its full effect without overstressing the structure. And since we didn't have to do the drape tendon for the principal tension, but we did want to restore the ultimate shear capacity, we went with CFRP sheets on the webs, and that's what you see here, the red stripes. And then the rest of the solution here, it was 5 tendons. You see in the bottom, tendons A and B are 7-strand tendons, and then C and D are 12-strand tendons up high. Now, the damage was on one side of the bridge, so it's an asymmetric solution. One of those top slab tendons, tenon D, is mirrored to the right side of the structure. Now, only tenon B required intermediate anchor block. So that's what that one looked like here. The other ones we cored through the diaphragm. We'll see those in just a minute. So this is what the new anchor blocks look like. We designed it, of course, per LRFD, but we used 8 threaded rods that had upper and lower plates to act as corbel steel. Now, they were immediately developed on the bottom side by using drilled and tapped holes in the partial depth, drilled and tapped holes in the lower plate that is outside the bridge on the bottom slab. We also used, for interface shear, 36 epoxy anchored rebars going into the bottom slab and into the temporary PT bar block, the erection PT bar block, roughened the concrete and added a shear key down at the end of it, at the toe end. We did use 6 near surface bars for the direct tension, and that's that bloom of red that you see in a finite element model that we were trying to resolve. It's a very lightly reinforced bottom slab, and those near surface bars are simply a groove that was dug into the concrete, filled with epoxy and a bar placed inside that. And then you got your typical bursting, spalling, steel, and then the anchor plate was designed as just your basic bearing plate, which is just for consistency with the anchors that we did on the diaphragms. It's important to note with this, though, so we followed PTI's design guidance on designing that from M50.1. This guidance was carried over from that relatively old document to the LRFD, but there was an error that was made in one of the definitions that will slightly undersize your plate. That error has been in there consistently up through the 9th edition of the LRFD. It has been fixed in the 10th edition, so make sure you use the latest version of the code if you ever have to design this sort of plate. And then we had an exit Diablo on the end to give Jason and his team a little bit of flexibility with the geometry. Now with the diaphragms, for its design, we had to do a stage strut and tie analysis to look at the vertical splitting that took into account the way it was originally constructed. So inside a closure pore, before there was a closure pore, you have the original tendons, and they impart some stress on those rebars on the exit face. And then you have additional stress that comes in with the later tendons that were stressed, and then, of course, the tendons that we're adding in. Now, we had to, of course, look at bursting here. You can see in the image on the lower right, those anchors are really close to the edge of the diaphragm face. You'll see why here in a minute. But so we designed them, the bursting per AASHTO, but then also went back and did a finite element model just to validate it. And so that's what you see in the top right there. The bursting stress is in orange. We took slices through that and then integrated the stresses to get the forces to calculate the amount of bursting we need, and then added CFRP sheet for that additional bursting reinforcement that was required. And of course the anchor bearing plate and then the cord holes, which I'm sure Jason's going to talk about here in a minute, again with exit Diablos for some flexibility. All right. This is the congestion we're dealing with inside that diaphragm as far as the post-tensioning. The top slab transverse PT I didn't show, but there's some more PT in there, but it's above where we were working. Our tendons are the green and purple in the top there with the anchors on the far side of the image, and then the orange below that on the bottom. So you see it's pretty well congested here, but this is really the one that had the pucker factor. The orange tendon here had to be cored between 2 existing bottom slab tendons. Now, we benefit here that we did have an erection PT bar hole that was in that location. So we knew where those tendons weren't, but that PT bar hole was not continuous through the diaphragm. Remember, there's a 2-foot closure pore in the middle of it, and the holes don't line up. They were several inches off. Yeah. So, but that did help us in guiding between those 2 tendons. All right, shear design, we used AASHTO guide spec for design of bonded FRP systems for repair and strengthening of concrete bridge elements. Thanks for the very short title there, AASHTO. But the equations are very familiar. These look like your regular reinforced shear equations. So it was very straightforward to design. But we ended up with 2 plies of 12-inch wide CFRP sheet on 12-inch spacing on both the interior and exterior faces of the north web. So just a few interesting details I want to point out here before I hand back over to Jason. We decided to use an unducted PT system. And for this, we used individually greased and sheathed strand. Now, this is the same strand that you would see in a lot of cable stay applications. It is the same strand, A416 grade 270 steel, but it has a corrosion inhibiting grease that's applied to it in a destranding operation. And then after that, a 50 mil HDPE sheathing is extruded onto the strand. Again, though, it's something we already had in the industry. It's already been tested. We're familiar with it, so we went with this approach. And the benefit was, obviously, avoided the needs of grouting that tendon, but we were, and it also makes the exterior strands, at least, a little bit more accessible for inspection. But it provides the same level of corrosion protection, maybe a little bit improved over, over a grouted condition through there. Interesting note, which we learned only about a month and a half ago now, this is, we believe, the first application of an unducted tendon system and a bridge superstructure in the United States. The second one was the Laurel Fort Bridge, and that was done about 6 or 8 weeks ago. I think they finished that one up, and they chose to use epoxy-filled and coated strands. So, interestingly enough, Structural Technologies was the contractor for both of those, and they could talk to you about the two different approaches for the unducted tendons. All right, we had long, straight tendons, so they don't go through deviators, so we needed to deal with the vibrations here. We did a vibration analysis that showed that basically we could support these on about a 40 to 50 foot spacing to prevent any issues. The steel, we used steel posts that had basically just U-bolt clamps and saddles. And then the particular detail that's important here, we're essentially connecting the bottom slab to the top slab. That's a lightly reinforced top slab and a lightly reinforced bottom slab. Very flexible top slab, though. We did not want to damage the top slab. We concerned about punching a hole through it. So the top connection there moves vertically. This got slotted holes. We used a low friction tape on the fang surface, and the bolts are left in there loose. So if you put your finger on it, it moves up and down, but it's restrained transversely and longitudinally. And then because we've got unducted tendons, there were some concerns about the strands vibrating individually. And also, we did not want, if a strand were to release, we didn't want it whipping around inside the bridge. So we used what we call containment sleeves, which are just a very rudimentary design. It's just a neoprene sheet wrapped in a split HDPE duct with stainless steel band clamps. They're just spaced every 10 feet, plus or minus, along the length of the tendons. With that, I'll turn it back over to Jason to talk about the implementation of this thing.
All right, I'll go quickly. I know we're approaching our time. So as Nick showed, and the WJE guys said the same thing, the carbon fiber applications for stiffening things up, where we're using it. So this is actually in the process of the carbon fiber being coated, and those anchors are very close to the face of the diaphragm. So if you ever have questions about how effective carbon fiber is, when you're willing to stress one of those or a couple of those tendons up and rely on your bursting strength to come from the carbon fiber sheets, you're putting your money where your mouth is. So we chose to do the inside first, mostly because there was like record rainfall in South Carolina at the time, and they hadn't actually had a dry week in I think 3 months, and then we were able to actually get outside immediately after that. So under lane closures, we could only close one lane down. So getting in on snooper trucks and access platforms, installing everything on the outside. We managed to hit the 1 week when we did this externally. We hit the 1 week where it stayed dry all week, and it was right before the temperatures dropped. So we were very fortunate in the timing of everything. There's a lot of logistics that go into that. As Nick had mentioned, the congestion through those diaphragms is pretty intense, and we also got a really good lesson on the limitations of GPR up front, where we think that the GPR technician may have kind of looked at the drapes and was worried about where the tendons were, and I think he drew tendons everywhere. So we almost had to throw the GPR away and realize he was probably picking up the regular steel and very likely imagining that that's where there were draped tendons. And then one of the things we had playing our advantage is actually taking the blocks off of those two existing anchors and making sure that they're where they were supposed to be. So we measured them based on the center line of the span, and it was within a 1/16 of an inch. I'm not sure that I hit the center line within a 1/16. So I was pretty convinced that the existing tendons and the anchors were where they were supposed to be. But as we were drilling, I think we were on the phone with Nick and his team through the night until I think we got the all clear like 9, 10 o'clock at night. But we were getting these models real time, sending between text messages of, okay, you're past the point where we're really worried. If you're this far in, we're good, and we were able to let it rip and finish that up. But drilling 10 feet through a diaphragm that's that congested can be a little bit nerve-wracking. Try not to make sure that the cure is worse than the sickness. And then, of course, those anchor blocks, as we poured them in, just where we were at, it wasn't feasible. The anchor blocks were big enough where they were fairly large pours, but they weren't large enough to warrant opening up a concrete plant in the middle of the night, doing lane closures and pumping in there. So we ended up doing bag mix with some USCP's self-consolidating concrete, which worked really well with all that rebar in there, and it bonds very well. And we opted to go fiber reinforced as well. I was just worried about something that high strength, having some shrinkage cracking and freaking people out before you stress it out. So the fiber reinforcement worked out really well. It was very dimensionally stable. We didn't have any cracking before or after stressing, which was great. And then these are just photos of the installation process. We're actually able to push all the strand in by hand. So that was actually pretty convenient. We originally went in, we were gonna do a monostrand ram to stress it, and we just discovered that we were getting pinching, which if we had a duct, we wouldn't have seen that. So we ended up dropping back and getting multi-strand ram and redoing that one tendon. We reran everything in it, and we were able to do that easily because we didn't have duct. And then installing those anti-vibration posts as well. Picture on the right of that, just holding everything together. It worked out really, really well. And then the anchors, Nick had mentioned, we're basically using like a stay cable system, really. And so we had anchors that we were able to, we have grease ports in those anchors, and we have some stop bushings and deviator bushings to make sure we didn't have any bunching of the sheathing, and we didn't have anything that was unprotected. There was, the bushings made sure that we just had a tiny little space between the anchors and where the sheathing stopped that we had to grease, and we had a grease port for that. We were able to fill all that up and then coat them, so we have plenty of corrosion protection on them. But that takes us here to the end, Q&A portion. Didn't leave much time, sorry.
Thanks. So before we open it for Q&A, I do want to hit just a few closing points. So hopefully the importance of incorporating replaceable tendon details was abundantly obvious here. We were able to replace those 1,000-foot-long tendons in a matter of days, whereas these shorter tendons, which were not a replaceable condition, I mean, it took us, it was months. Go from, obviously being able to replace those tendons in days, getting the bridge back open, also much cheaper. So hopefully the importance of replaceable tendon details was obvious. Second, and this is more directed to any owners that may be here, but especially after you see a presentation like this, I really want to stress that these sort of bridges are really the exception, even from that pre-2000 time period. Most of our post-tension structures are performing quite well. And the industry's learned a lot since that time. We've come a long way with far better material, construction, and design specifications are a lot more comprehensive, and just our standards and practices and details that we have in today, and the training for grouting and post-tensioning installation. The modern day segmental, post-tension segmental bridge would not it would be extremely unlikely for it to suffer the maladies that we had here on the Wando, and just a handful of others from its era. And then also, hopefully we were able to show that if you do have this situation, you've got to have post-tensioning or strengthening. There are multiple ways that you can do it. It is possible. I think the fourth thing I want to say too is these sort of strengthening projects, having a contract method, particularly CMGC, where you can get the designer and the contractor working together, really works out to the benefit of the owner. We are able to come up with a lot of out-of-the-box solutions, like unducted tendons and a number of other things. You're working together with the contracting team. So if you ever have to do this, I really recommend an approach like that where you get the designer and contractor together from the start. And with that, we got 27 seconds, but we've also got 30 minutes here before we go to go on break. So we'll open up for any questions you got.
You may have said it, but I might have missed it, but how were you made aware of the initial tendon rupture?
The very initial one in 2016?
Yeah.
Inspection.
Oh, okay. Easy enough.
It was, yeah, it was just routine inspection. They found the tendon laying on the floor.
So our two firms have talked about the capacitance testing and the magnetic flux leakage a good bit between each other. Can you just give me you guys' impressions on that data and how you utilize that data?
We did not find any significant findings with either system. So with MagFlux, we did find locations where there was some section loss, but as we had investigated it further, it was more often than not, it was local necking that happened during construction. And it was, be like, you could find the necking on one wire. I mean, that's kind of, what we're seeing there. It did not find any significant issues that we weren't already aware of. Now, there's some limitations. It can only scan in the free length. You can't get into what's inside, what goes into the bottom slab, top slab, or more importantly, what's inside those deviators, or diaphragms rather. And then for the capacitive probe testing, again, kind of the same story. We didn't find significant issues with it. We found a lot of voids, but more often than not, it was a really small void that runs along the top side of the tendon that's just not an issue. So.
Ductless situation. Do you anticipate the same sort of progression happening with external PT?
Say that one more time, sorry.
I said with the stay cable technology for the ducts, there was early days, everything was grouted, right? And then it's migrated towards this ductless where you can replace single strands. Do you anticipate the same transition occurring in PT bridges now that you've broken this ground?
We could. These tendons, it still wouldn't be able to easily replace a strand. Not in the method that we used here, and not in the epoxy filled and coated strand, simply because of the way the anchors are done. Like if I need to replace a strand that's in the middle of that bundle, you can't do it. Because you got your whole bundle is all together, and you'd have to feed it through, and it's. I don't see it being able to be done there. We could develop a design that I think that could be done, but your post-tension cables are going to end up being a little bit bigger, and we'd have to modify the design of the anchors. But it also, we can talk more. But no, you wouldn't be able to individually replace these strands. Now, removing the overall tendon might be easier, but. Yeah. Alf, did you say something about vibration too? Okay. All right, any other questions?
Well, I'd like to add one. So there was and I think it was your question about the corrosion cell.
Yeah.
Potentially with the grout. Because I deal a lot with corrosion, cathodic protection, things like that. That is an advantage to using this impregnation system, because if you don't know the quality of the grout or it has a lot of sulfates in it, if the quality of the old grout is really bad and you go and put a high pH new grout, you do create a corrosion cell between those two. And if you're worried about adding a corrosion cell along the strand, obviously you can't do a conventional cathodic protection system either, because with the steel being stressed, hydrogen embrittlement would be you'd induce it right away if you tried to do a conventional cathodic protection system. So using this injection method actually is a really good way to make sure you're not inadvertently putting a corrosion cell in, and also making sure that you are protecting it. It's a pretty low cost insurance, for some of these older bridges with suspicious grout.
Yeah. All right, so thanks a lot, Jason.